And in the elements, for bulk elements or neutral elements, the number of electrons has to equal the number of protons. But we have a third particle in there, the neutron. What happens with that? And the neutron can change some. There's no fixed number of neutrons in an element. There are some limits, but those limits, we have to study nuclear physics to identify what those limits might be. But when we change the number of neutrons, so we don't affect number of electrons, but we just affect mass. So neutrons have mass, so when we change the number of neutrons, we have a different mass associated with that element. So when we have atoms with different number of neutrons in them, we call those isotopes. And we can end up with different masses of these elements. And on the periodic table, what we do is we do a weighted average of isotopes found in nature to give us our atomic mass for the element, which is why that mass is not a whole number, because it depends on how much of each isotope is present in nature. So if we want to identify isotope, for most of chemistry we don't worry about isotopes. But we do worry about isotopes for a variety of purposes. Some isotopes are radioactive, meaning they are not stable, and they'll either absorb something or throw something out the nucleus and turn into a different element. So these radioactive isotopes we might use for medical imaging, such as PET scans, or we might use them for medical treatment to treat hyperthyroidism or other illnesses. So when we need to identify the isotope, one way is to just name the element followed by the mass number. The mass number is the total number of nuclear particles. That means total number of protons and neutrons. So for our isotopes are different isotopes of one element. Will have the same number of protons, same number of electrons, and same chemical properties. But the isotopes will differ in number of neutrons, the mass, and certain mass-related properties, such as diffusion of the element. And they also differ in nuclear stability, so some are stable and some are radioactive. Another way that we can identify isotopes is using atomic notation. So atomic notation uses the symbol of the element and then two numbers associated with it. The atomic number, which is represented by the letter Z, and that's the number of protons in the nucleus, and the mass number, which is represented by the letter A, and that's the total number of protons and neutrons in the atomic nucleus. So it's the total number of particles in the atomic nucleus. So these are both just whole numbers. And what we do is we use the atomic number as a left subscript and the mass number as a left superscript. So these two numbers will identify any particular isotope. And this atomic notation is a little redundant because the left subscript matches the symbol of the element all the time. So for lithium, it's always atomic number 3. Atomic number 3 is always lithium. So this combination is a little redundant, but that's okay. So when we have the mass number and the number of protons. When we want to get the number of neutrons, the number of neutrons is going to be mass number minus number of protons. So total number of particles minus protons will give us number of neutrons. For neutral particles, electrons will equal number of protons. We will be also being seen ions that have either a higher or lower number of electrons, leaving the atom with a charged species. So the mass on our elements, mass in general, we need a standard to define mass. So for atomic mass, for mass of atoms, molecules, we had to define our standard here. So we took one isotope of carbon, carbon 12. So carbon is atomic number 6, so it has 6 protons. Carbon 12 has a total of 12 particles in the nucleus. 12 minus the 6 protons means it will also have 6 neutrons. So it has 6 protons and 6 neutrons. We defined the mass of this carbon 12 as having a mass of 12 atomic mass units. We abbreviate that as AMU. In Europe, they tend to abbreviate it as U. So 1 AMU is a mass of 1/12 of carbon 12. So carbon 12 has an exact mass of 12 AMU by definition. However, all other isotopes are not going to have an exact mass associated with it. There's going to be some slight variations in there. So magnesium 26 has a mass of 25.983. It's close to 26, but it's not equal to 26. The difference in mass is called the mass defect, and we will look at that next semester. So to assign a mass to an element, we want the mass to be relative. So when we go out to the town of Boron, scoop up some boron from the playa, or scoop up some boron compounds from the playa, extract out boron, and weigh the mass, we want the mass to be close to what we say it is on the periodic table. So since there are more than one isotope of boron, if we just did a simple average of the masses of each isotope, we won't necessarily get what we find on that playa. So a simple average is what we normally think of as an average. So we add up all the masses divided by the total number of masses that we add up. But that's not going to give us exactly what we want. So what we use instead is called a weighted average. So a weighted average is we're going to take the mass of each isotope. So that's our value for our weighted average. And then we're going to use a weighting factor. And our weighting factor is the abundance of that isotope. So what we do is we look at different sources of boron. We do it globally. And we determine how much of each isotope is present. And that becomes our weighting factor. A fraction of how much of the isotope is present in the global total. So we multiply the mass of each isotope by its fractional abundance, and then we add this up for all the isotopes present. So using boron as an example, there's 19% of boron 10, 81% of boron 11. Now the masses of boron 10 and 11 aren't exactly 10 and 11, but they're close. So we can use this as our example anyway. So we use 19% in a fraction is 0.19, 81% in a fraction is 0.81. So 0.19 times our 10 AMU plus 0.81 times 11 AMU gives us 10.81. And this is a really close agreement with what's on the periodic table, 10.811. We just have to increase precision to get that additional decimal place. And when we go to different sources of boron and we extract the boron and weigh the mass, we might find 10.81. We might find different amounts, different masses associated with the boron. because we're doing global average and the different sources don't always have the same percent abundance. And when they don't have the same percent abundance, it means that there's some additional information in there about that source. And then when we, if possible, we might be able to identify the source of that information and identify what that information is. And using the slight differences in percent abundance of isotopes, we can do radioactive dating of artifacts, carbon-based items, rocks. We can identify if things come from the Earth or from outer space or from Mars or from Moon. So when the percent abundance changes, there's information that can be had from that change in abundance. So after we define the mass of a mass unit, atomic mass unit, that we can use for atoms and molecules, well, that's great. We can talk about the masses of atoms and molecules, but we don't have a scale built that we can use in the lab that can measure atomic mass units. It's too small of a unit for us to use on the laboratory scale. So we defined two additional quantities that allow us to work on the macroscopic scale. So we went back to that isotope of carbon, carbon-12, and we defined a number called Avogadro's number. We represent it with N, capital N or capital N sub A. And what we said is that 12 grams of carbon-12 has Avogadro's number of atoms in it. When they made the definition, they didn't know what that number was, and we have since been able to measure it and determine that it's 6.022 times 10 to the 23rd atoms of carbon-12 and 12 grams of carbon-12. And then we defined another quantity called a mole. And a mole is the amount of anything that has Avogadro's number of units in it. So if we have Avogadro's number of baseballs, we would have a mole of baseballs. And if we look at that carbon-12, that means that we have 12 grams, Avogadro's number, so we have a mole, so we have 12 grams in a mole. But one atom has a mass of 12 AMU. So the number is the same, but now we can use a macroscopic unit of grams per mole. So mole is Avogadro's number of units. Avogadro's number is 6.022 times 10 to the 23rd units. Units could be atoms, molecules, electrons, whatever is appropriate for us. So we have defined this, that the mass on the microscopic scale, atomic mass units, is equal to, in terms of numerical value, the mass on a macroscopic scale in terms of grams per mole. Now this mole is just a big number of atoms. Like a dozen is 12 donuts. A gross of paper is 144 sheets of paper. So it's just a big number of atoms or molecules. So when we look at chemical reactions, and we see how many atoms or molecules will react together, we scale that up to a mole, and we get how many moles of the atoms or molecules will react together. So mole is going to become our central unit for amount of substance. And now, with our new definition, our mass on the microscopic scale will give us how many grams are in 1 mole of the substance on a macroscopic scale. And that is the end of this chapter.